Circular joint, right? Okay. Then what I'll do is maybe pending the questions. Yeah, I don't think anybody. Yeah. Okay. Do you see both the students will join? Names? No. Good afternoon. Good afternoon, Rahul. If you have any specific questions, please put in the chat box. I'll clarify. Good afternoon, Mahmood. What is the difference between powder mat and emulsion mat? This is relevant. I mean, reference to which? Did I teach anything like that? This with reference to which thing? I don't think I have even I have used these terms anywhere in my lecture. Is it with reference to any of the lectures? Please let me know. I think I have not used these terms. Sound is not clear, is it? You have asked what is the difference between powder mat and emulsion mat. Did I actually use this term anywhere in my lecture or anyone in any module? I don't think so. Please be specific. If you, I mean, from which module you are asking the question. I don't think this I have used. Since this is with reference to the fabrication or manufacturing of lamina, but you are asking from which module? I don't think I have used that. Assignment 5, question 8 and 9 in details. Or then I have to see this assignment 5, question 8 and 9. Could I see that? Yes, wait, let me see. Question 8 and 9, the unidirectional glass epoxy lamina, the Young's Moduli and Poisson's ratio of the fiber and the matrix are given. Okay, and those are, yeah, it's given. The ultimate strengths are also given. Yeah, the minimum volume fraction is. So if you see, while we have discussed the longitudinal tensile strength of a lamina, we have actually derived an expression for V critical and V minimum. If you remember correctly, I am just telling you again what is V critical and V minimum. Why we add fibers? We add fibers to matrix, and it is expected that addition of fiber will actually lead to improvement in the strength. Now, it depends what will be the strength of the composite when we add fibers. It depends upon the, besides fiber strength and matrix strength, it depends upon the relative proportion of the fiber, which is the volume fraction. Okay. Now, suppose what are the limits? If you remember, I have discussed that in details. The limits could be Vf is equal to 1, that means all fibers, then it will follow the stress strain behavior of the fiber. Other limit could be Vf is equal to 0, that means all matrix, then it will follow the stress strain behavior of the matrix. And actually the stress strain behavior of the composite will lie in between. And where it will lie, that is decided by the volume fraction. Now we have derived that there is a critical volume fraction. If the volume fraction is less than critical volume fraction, the longitudinal tensile strength of the lamina will be less than the ultimate strength of the matrix. That means the basic purpose is not served. By adding fibers, it does not improve the tensile strength of the lamina. That was V critical. And there is another term, V minimum. What was the significance of V minimum? If you remember, V minimum was that if we add, suppose we had only one fiber in a bulk of matrix, what might happen is that when it's strained, that fiber might fail. And even if that fiber fails, that fiber is actually carried away by the matrix. What is the amount of matrix? If we say if we add only 1% fiber, that means 99% is matrix. So 99% of the matrix, that strength of that 99% of the matrix is more than the strength of the composite. Okay, so that is what is actually the minimum volume fraction, and those expressions are derived. And let me assure you, you don't have to remember those expressions. But why I given is just to have an understanding. This the objective of this question, the assignment is once you calculate that, you can actually see what is the minimum volume fraction. Suppose it comes out to 5%, then you'll have some idea about what is the range of minimum volume fraction. Having said that, please be informed that this minimum volume fraction or critical volume fraction is actually decided by what is the fiber strength, what is the matrix strength, and their relative proportions. I think just this is very simple. You just put all this data in the formula and you get what is minimum volume fraction. Similarly, the next is 9 is critical volume fraction. So you have the expression for VCR in terms of all these properties. You just put those values and you will get V critical. Now it is straightforward, just to put those values and you will get the answer from the expression. But the objective of giving this is that you will have a feeling of what is the range of minimum and critical volume fraction. I hope that is clear. Is that clear, Mahmoud? Thank you. So any other question? Yeah. In between, I just tell you that in the module 7, module 6,
Lecture
in module 6, that when I have actually where I have derived the coefficient of thermal expansion of lamina in terms of the coefficients of thermal expansion of the fiber and the matrix. Similarly, the coefficient of moisture expansion. Please look at the expression for beta 1. At the end, I think it is around 39 minutes 9 seconds. The denominator, by typographical mistake, it is EF. You can make out this actually. It is just it should be E1. Please make a correction. Beta 1 is equal to, the numerator is there, and in the denominator it is EF into something. It will be actually E1. And if you see if you follow the derivations, I think it will be clear. It is just while typing it became EF. It will be E1. Yeah. Sir, in the examination on screen calculator will be difficult to solve numerical. Can we get prior examination access of? Let me assure you, in the examination we are quite aware that you have only access to your screen calculator. Therefore, whatever little calculations are required, we take care of that. That it is sufficient for you to. I mean, the screen calculator is sufficient to do that. And again, I have told you that you don't have to. In any examination for that matter, all these, this formula and all these things you don't have to remember. If there is a long formula, that will be provided. Okay, only very small formula like say E1 is equal to EF VF plus EM BM, 1 by E2 is equal to VF by EF plus VF by M. This formula sometimes we ask. Other than that, all these long expressions you don't have to remember. And calculations, I am just emphasizing again, calculations will be, if at all there is some calculations, we'll make sure that it is sufficient, time is there, and the screen calculator is sufficient for that. So material property symmetry. Did you see that, did you actually go through that module where I have actually taken the material property symmetry I have discussed in details? Now, because I have to draw in that case the full thing. So, let me ask you, do you understand the geometric or dimensional symmetry? You understand the symmetric figures, right? Kaushik? Okay. Then suppose if you draw a symmetric, suppose I draw a rectangle which is symmetric, which has both axes of symmetry, planar figure, a plane figure. Okay. Now I pull it in one direction. Okay. Then I rotate it by 180 degree. Again pull it. If the deformation behavior is same, that means that plane of rotation is one plane of material property symmetry. Could I make it little clear? You take a rectangle which is perfectly symmetric. I am giving an example of a planar figure. You can just extend that to three-dimensional figure. Suppose if you draw a rectangle and you pull it in one direction, suppose it is subjected to tension, so it will have a deformation. Okay. You rotate it by 180 degree, again pull it. If it is same, that means that plane about which it is rotated is the plane of material property symmetry. Is that clear? So this is exactly what we have done. What we have done is we have rotated and then made sure that C matrix does not change because of rotation. First, what we have done, we have taken an anisotropic material and then just follow that lecture. Otherwise, I will tell you again. Next time, maybe I will draw a figure and tell you. You just follow in the video. What we have done was that we have actually taken an object and we have defined the stiffness, of course, with reference to x, y, z. And then what we have done is we have changed z to z prime. Basically, we have rotated that by 180 degree. And then in the stress strain behavior, we have taken it that the stiffness matrix is same. C matrix does not change. Okay, why it does not change? Because even if you rotate with respect to that z by 180 degree, it does not change. That means that is a plane of material property symmetry. Then when it came to orthotropic, we have made another perpendicular plane in the similar way, and that is how we have actually derived the number of constants, independent elastic constants required for say material having one plane of symmetry, which we termed as monoclinic. Then material having two perpendicular planes of material property symmetry, and of course that I have also discussed that guarantees the third plane also material property symmetry, and that is orthotropic. So what I suggest is you take the example of a geometric symmetry and then you apply a load. Just visualize that if I rotate it by 180 degree, apply the same load, if the behavior is same, that plane of rotation is actually a material property symmetry plane. So if not, I have another this thing, live class on 21st or 22nd, I suppose. So you remind me, maybe I will come with it because I have to draw that and then I can show you. Okay, it will be more clear. I think, is it clear, Kaushik? Okay, I think he has already responded. Thank you. So any other question? Thank you, Kaushik. Okay, if somebody has asked a question I have seen in the forum, yeah, any question? Sir, why we made assumptions before doing tests? Which tests? Which test? Before, I could not get your question. Please, can you just elaborate? Why we made assumptions before doing tests? Which tests you are referring to? Please clarify. Which assumptions, by the way? Can you just tell me in the module with reference to the module, which assumptions you are talking about? Oh, not test, classical lamination theory. See, I'll tell you, like, if you look at the assumptions in the classical lamination theory, each assumption is actually having a meaning. If you remember, I have discussed each and every assumptions one by one. Now, in classical lamination theory, basically see, a large number of lamina are actually stacked together. Now, one of the assumptions is perfect bonding. Say, for example, if you ask me why we have taken this assumption, of course, it's not that I have made these assumptions. Why in classical lamination theory these assumptions were made? Try to understand the implication. If there is not perfect bonding is not there, what does it mean? That means the two lamina will have different displacement. That the lamina can slip over each other. Okay, and the basic idea of this classical lamination theory, why the classical lamination theory was developed? Basic objective has been to establish a relation between the stresses and strains. In macromechanics of lamina, we have established the relations between stresses and strains because that is what exactly is required for design and analysis of any component. Okay. Now, in classical lamination theory, the fact that each layer is having different properties. Okay, each layer is having different properties, so it's not that easy to relate the stresses to the strains. Okay, so we started with a perfect bonding. That means as soon as we talk about perfect bonding, that means they are compelled to displace by the same amount subjected to load. Okay, if you apply an axial load, they are actually displaced by the same amount. Okay, and then if you just follow at the end of these assumptions, I have also told you actually in how we apply the strain displacement relations and the compatibility conditions. By if we do so, it's actually complicated in classical lamination theory. Therefore, what we do is one is the assumption of perfect bonding, and in the second, suppose if you ask the plane section remains plane. Okay, what is that assumption? That means we are actually not considering the shear deformation. Okay, so I have also explained that what is the consequence, what is the implication of not considering shear deformation. In actual practice, depending upon the thickness, if it is thin, we might still consider this assumption to be justified. Depending upon the thickness, that shear deformation assumptions may not hold good. Okay, that there is no transverse shear strain, there is no transverse shear strain might not hold good. So, of course, in this course I have not discussed. So, there are ways to actually treat that. That means, in classical lamination theory, we can actually put the shear deformation to have a more accurate solution specifically for thicker laminates. But having said so, with these simplified assumptions, the classical lamination theory gives us very, very important information. What are those? See, we could actually characterize a laminate. We understand that when it comes to the in-plane behavior of a laminate, it does not depend upon the stacking sequence. It only depends upon what are the number of layers. So this is an important conclusion from if you look at the A matrix, okay. And we also understood that we could appreciate that depending upon the stacking sequence, how you actually stack the lamina, you can actually obtain the desired the requirement of strength and stiffness. I have given an example number of times. The most simple example of understanding that is that suppose we want that a laminate. See, in a laminate, all these layers have their. Why should we put a 0° layer where you want the strength in the x direction or stiffness in the x direction? If we want strength and stiffness in the y direction, of course we'll have to place 90° layers. If we expect that the laminate has to actually withstand shear load, obviously you have to put plus minus 45° layer, because we have already discussed that, and we have derived that plus minus 45° lamina actually are strongest in terms of resisting the shear. Okay, so each of these layers have their own functional requirements, but when they are put together, now depending upon what kind of behavior you want, the stacking sequence plays an important role. So that is the importance of classical lamination theory. Even if it is actually based on some simplified assumptions, you get important information from that. Okay. Now another example is, suppose you want a laminate which is strong and stiff in both the directions 0 and 90, which is also strong and stiff against shear, but at the same time you want it to behave like isotropically. Go for quasi-isotropic laminate. What a quasi-isotropic laminate? I think I have that has been defined in your. You can just go back to the modules and see. That means if you take a 0 plus minus 45 90, this is an example of quasi-isotropic laminate. It ensures you that under in-plane loading, it behaves like an isotropic material. Therefore, even though the classical lamination theory is based on certain simplified assumptions, but that gives us, with a simple analysis like the concept of force resultant and moment resultant. Why we have to do that? Because each layer will have different stresses. So it is very difficult to correlate the stresses and strains for the entire laminate. Therefore, the concept of force and moment resultants were used. Okay, wherein we have assumed that the force resultant actually acts at the mid-plane, which is nothing but the sum of all the stresses integrated across the thickness, similar to the moment resultant. And then the force and moment resultants are actually related to the mid-surface strains and curvature. And once we establish the ability matrix, that actually shows the full character of the laminate. Okay, so that is the beauty of the classical lamination theory. Even though like some of the assumptions may not hold good, like as I told you just now, that there is no transverse shear strain depending on the thickness, that might not hold good, but that could be incorporated. That of course beyond the scope of this course. Could I make it clear a little bit? Could I convey what I wanted to tell? Please respond. Goshik. Also, I will make a point here. See, always try to make a distinction between assumptions and restrictions. Assumptions are, to some extent, we justify some specific cases. Restrictions are different. Say when we say that that it is linearly elastic, that means we are restricting our discussion to the linear elastic behavior. Okay, so this is a kind of restrictions. And assumptions are to some extent, like this is an assumption that no transverse shear deformation. Okay, then perfect bonding, that means the two adjacent layers or lamina are not allowed to slip over each other. So these are assumptions. Okay, and there are restrictions also. We restrict our discussions to only linearly elastic cases. Thank you, Goshik. Any other question? I think somebody has asked a question because it's in the same laminate analysis. that how come I have given you an example just showing that how complicated the laminate analysis could be otherwise. I have taken, I think in that same lecture, I think module 7, lecture 1, one example was a 0 degree and 90-degree layer, and I have written there that the strain along x in the 0 degree and the strain along x for the 90 degree are same. But somebody, I don't remember the name, somebody has asked how could the strain be same. Again, the strain is same because they are perfectly bonded. Okay, in all our assumptions, it's perfectly bonded. So if the two layers are glued together, they are perfectly bonded. If you pull, naturally they will be pulled, they will be extended by the same amount. Okay, but okay, given a free hand, I mean, given if the two materials are different and they are pulled separately, definitely their extension should be different depending upon their Young's modulus. But here it is same. So why we not often analyze an isotropic laminate in our course so far? Anisotropic laminate. What is anisotropic? Let us go back to the definition. What is anisotropic? We have discussed in details. No planes of material property symmetry. Okay. Then what is orthotropic? I am straight away coming to orthotropic. Three mutually perpendicular planes of material property symmetry. How did you give example of orthotropic? Example of orthotropic material was a unidirectional lamina is an orthotropic material, right? Why do you think a unidirectional lamina is an orthotropic material? Because the fibers are laid in a particular direction and the fibers are very strong and stiff along the longitudinal direction, and it's in the transverse direction it is not that strong and stiff. Therefore, if you talk about a lamina, it's an example of a orthotropic material, and we are discussing here the courses on fiber reinforced polymer matrix composite, and this lamina, unidirectional lamina, are all orthotropic lamina. Therefore, the laminate is actually made of stacking such orthotropic laminates and orthotropic laminate. Now, what did you actually talk about anisotropic laminate? It's not clear to me. Okay, now I can make a laminate of two isotropic materials. Okay, there are examples which are used for different purpose. Okay, but that is not the objective here. Okay, I mean, you make generally we do not call it a laminate. There are, suppose if you take two thin sheets of, one is aluminum, another is steel, and glue them together, these are two isotropic materials. Okay, so like for example, bimetallic strip. Okay, but these are not called laminate. But since we are discussing here the course is on fiber reinforced polymer matrix composite, FRP composites, so the laminates are actually made of unidirectional, or in this case we are discussing unidirectional, so orthotropic lamina, and therefore it's an orthotropic laminate. Is that clear? There's nothing like, see, the unidirectional lamina are always orthotropic. I think if you are confusing between the angle lamina and special orthotropic lamina, angle lamina is also orthotropic. Only thing is, when you load an angle lamina with reference to the xy or the global axis, which do not coincide with the local or the material axis 1, 2, then apparently it looks like that it's anisotropic. Basically, in that the shear extension coupling terms are present. Okay, Q1 6 and Q2 6, but actually it's not anisotropic. I told you, I discussed that in the class earlier also. If we know the 4 independent elastic constants and if we know the angle, you can find out those. So its behavior with reference to xy or the global axis is though seemingly anisotropic, but with reference to its material axis it is still orthotropic. Thank you. Any other question? Again, with this reference to Mahmoud Alam's that you might think that in assignment there are some questions where you need calculator. Because this course is actually on mechanics, so I think in the first introductory lecture I told you that until or unless you actually solve problems, you are actually not trained properly in this course. Therefore, the assignments have two objectives. One is, of course, I mean, it's a kind of tests where you solve this problem and give the correct answer. Also, that because you are doing it at your home, you have, access to calculator now. Do that problem, okay? So that you also practice, because this is a mechanics-based course. So therefore, even though there may be one or two problems in assignments it might look like that you cannot do without your scientific calculator at hand. May be true, but this has nothing to do with the exam. Exam, we are quite aware that you have only access to your screen calculator. Therefore, the questions will be according to that only. But what about that question? It was not asked after the propulsion mat and emulsion mat. Who asked the question? I think it has something. Powder mat and emulsion mat.
Is referring to matrix?
No, nothing to do. But I think I have not discussed that any time. Maybe that is to do with the fabrication of. How many are there in the meeting?
Yes, sir. What is Poisson ratio? First of all, it is Poisson's ratio. Okay. What is Poisson's ratio? I think that is okay. I'll tell that. You take a axial member, load it longitudinally. I mean, load it along the axis. So what do you expect? Along the axis, there will be extension if you are pulling it. Okay. And there is a corresponding contraction in the lateral direction. Suppose if you take an axial bar of say rectangular cross section, if you just pull it along the axis, there will be extension along the loading direction, and perpendicular to that there will be a contraction. That is because of the Poisson's ratio, which is called Poisson's effect. Now, how we define is, suppose if you apply a load and your longitudinal strain, meaning the strain is in the direction of the load, the strain is change in length per unit length. Suppose we call it epsilon L. Okay. So the ratio of the lateral strain, that means epsilon T T, that means the transverse strain, that means perpendicular to the longitudinal direction, to epsilon L with a negative sign, okay, is the Poisson's ratio. I think that the definition of Poisson's ratio is there, I think maybe in +2 also nowadays. I think in higher secondary course also it is there. But this is how it is defined. But why I have defined it repeatedly in this course is that it's important to understand the definition of Poisson's ratio when it comes to orthotropic lamina. Now, this is the definition of Poisson's ratio which we know in our +2 level. But when we define Poisson's ratio, the more precise is that if you apply a load or stress along X, that is the only load, and there is no other stress. If you just go back and see in the lecture, I have written it number of times. Nu xy, which is the Poisson's ratio, nu xy means when stress is applied along X, and the ratio of the strain along Y to strain along X is the Poisson's ratio nu xy. That is the definition of Poisson's ratio. Okay. Similarly, if we apply a load only along Y, no other load is applied, then the ratio of the strain along Y, strain along X, epsilon X divided by strain along Y will be nu Yx. So it should be, I mean, for isotropic material it doesn't matter. We just write that nu is equal to ratio of the lateral strain to longitudinal strain. Okay. Now, because the strains are direction dependent and the properties are direction dependent in the case of an isotropic material, therefore, in case of an isotropic material, we have to define Poisson's ratio like nu xy, nu yx. They are not equal. Of course, they are related. Nu xy and nu yx are related by the ratio of ex by ey. So this is the definition of Poisson's ratio. Please go back and check if you are not clear about Poisson's ratio. Check any physics book +2. At least the definition will be clear. Okay. Or should I write? I think it's not required. Poisson's ratio. Are you not clear? Please let me know. Otherwise, I can write for you also. Please let me know if it is not clear.
Last class one unanswered doubt was the glass transition temperature.
But he is there.
I don't know.
Then leave it there. Thank you.
Is there in the lab session asking regarding glass transition temperature?
Why it is not there?
I don't know. It's roughly the same.
Somebody has asked about glass transition temperature in the last this thing. So see, for glass transition temperature is, I mean, above glass transition temperature, it becomes suddenly very soft. The material becomes very soft, and below glass transition temperature, it's like a glass-like material. Okay. Therefore, in polymers, what happens is we always try to see that the operating temperature should be below glass transition temperature. Otherwise, what happens? It becomes too soft to be used as a structural material. Okay. And I think I have discussed this glass transition temperature with reference to the hydrothermal effect. Therefore, what happens is that when that moisture is absorbed, then it influences the glass transition temperature also. That is what the idea of discussing glass transition temperature was. I think I have drawn the card for dry and wet condition. Okay, So this is the significance of glass transition temperature. Below glass transition temperature, it's like a glass kind of material, it's kind of brittle material, and just above glass, I mean, when the temperature is, the glass temperature is exceeded, then it's like rubber-like material, it's very soft. Okay, that's what it is. Residual stress. I think I have discussed that with reference to again hydrothermal stresses. See, what happens is, consider a fiber embedded in a matrix. Okay. So the coefficient of thermal expansion of fiber is much smaller compared to that of the matrix. Okay. Now the fiber and the matrix is perfectly embedded. That means the interface is perfectly bonded. Now you increase the temperature. What happens? Because they are perfectly bonded, they extend because of this delta T by the same amount. But given a free expansion, the matrix would have expanded by a larger amount compared to that of the fiber. So for the matrix, the expansion is constrained. So the matrix is under compression. For the fiber, the expansion is more than its free expansion, so the fiber is in tension. So this is the residual stress in the fiber and the matrix. But there is no mechanical load, total load is zero, therefore sum total of these forces will be zero. That's why it's called residual stress. Unrestrained and restrained means, suppose you have a lamina, say, okay? You keep the lamina on a table. Lamina means it's a piece of paper, say, okay? Suppose you have a A4 size paper, you put that paper in the table. Now if you neglect the friction between the table surface and the paper, so this paper is now free, okay? So this is what I mean, it's unrestrained. On the other hand, suppose you use some glues and attach that sheet of paper to the table. So this is fully restrained. Now it cannot, okay, even if you increase delta T, it cannot, expand or contract. Therefore what happens is, there will be stress. Now if you consider a laminate, there are a number of lamina stacked together, okay, and they are perfectly bonded. Therefore each lamina is actually constrained. It is not free, okay. It is constrained. It is actually bonded to its adjacent lamina. So this is what is called unrestrained. And also suppose if you say a simple rod and attach its both the ends, suppose weld it to some supports, okay. So its both ends are actually restrained. Now even if you heat that rod, it cannot expand or contract. So this is restrained in a particular directions, okay. See, I have not discussed metal matrix composite here, excepting a very brief introduction in the beginning, and I told that this course is on fiber reinforced polymer matrix composite structures. Therefore, I restricted the discussion. But having said so, I think I have discussed few matrix materials and reinforcement materials for metal matrix as well as for ceramic matrix composites. But analysis of metal matrix composites and ceramic matrix composites are beyond the scope of this course. Therefore, I did not discuss anything. But only thing in the introduction, to start with, before coming to the fiber reinforced polymer matrix composite, we had a general introduction to composite materials. So far, we have discussed different types of composites. Then I have mentioned what is a metal matrix composite, what are the fibers, what are the reinforcement, what is the ceramic matrix composites. Even we have discussed what is carbon-carbon composites. Okay. So we have not discussed this metal matrix composites here. This is beyond the scope of this course. Of course, if you want to know more about metal matrix composites, you can just refer to Paul's book or Jones' book, or maybe there are other books also, like Malik's book. You can see that a detailed description will be there. But in this course, it is not in the scope of this course, because here we are basically discussing the mechanics of fiber reinforced polymer matrix composites. Any other question? Otherwise, 7 minutes left. Now, for metal matrix composite, different types of matrix and the fibers like silicon carbide and all these I have given a brief description, but one can see other books on composite materials. These two books are actually for fiber reinforced composite mechanics. Even in Kauf's book, I have given those examples of metal matrix and ceramic matrix and carbon-carbon composite from Kauf's book only. You can refer to Kauf's book for a brief introduction to metal matrix composites. I think I have given the name of that book also in the. Why moisture expansion of fiber L1 0, not in the case of thermal expansion? Fibers are insensitive to moisture. It does not absorb any moistures. Okay, because it's not organic, so it doesn't. These are inorganic fibers mostly. It doesn't absorb any moisture. On the other hand, thermal expansion coefficient is there. Okay, it is basically moisture expansion coefficient depends on if it's a porous material, its moisture expansion will be more. Therefore, the moisture, it's insensitive to moisture, and therefore the moisture expansion coefficient of fiber is 0. But fibers do have thermal expansion coefficient. If it is heated, there will be change in its dimension. Therefore, thermal expansion coefficient is not 0. But of course, compared to matrix materials, it's much less. So if there is no other questions, thank you. We'll meet again in the next live session.